Okay, so in this session we are going to talk quickly about STD mdspan, and that might be part of an answer to a question that was shown yesterday about what should you do for your matrices. Maybe you will see why. So what is the motivation for mdspan? So basically there is, before mdspan there's nothing in C++ that really allows you to deal efficiently with multi-dimensional data, especially if you have requirements on how the memory layout should be. Like if you're dealing with this kind of stuff in HPC, you are fully aware of that. You might have your data in C layout or in Fortran layout, and you're interfacing between them, and then memory layout is different. Your algorithms have to be written in a different way because of all that. And yeah, so if you are in HPC and you're dealing with multi-dimensional data, you're probably doing these three things that are mentioned here on your own. You're re-implementing stuff. You're re-implementing your allocation of multi-dimensional data because you want it to be allocated on for CPU, for GPU. You want to make sure that alignment is good in all cases, and you want to make sure you have the right layout for the hardware. Then you want to access this data, and so you're abstracting the layout to be able to use it in the same way, so that the first index means the same in whatever layout you have underneath. And then you are implementing your iteration over that stuff, algorithms over this multi-dimensional data. And this is, I mean, most cases you have to do that because that's what you're doing in this domain-specific algorithms, probably highly optimized. When you're doing all of this on your own, maybe there's some libraries that are used sometimes, but many projects do it on their own. And now what do you do if you want to interface between these libraries? I mean, it's hard, right? In best case, you have well-defined, well-described concepts of your multi-dimensional buffers, and then you can try to model these for the other library. And in the worst case, probably it's a very concrete class, and you basically cannot use this other library. And to this question, mdspan. Oh, there's a typo here. mdspan without the columns in between is the answer. This is a non-owning multi-dimensional array view, and is meant to be in the interfaces of libraries. Because basically you have this view over your multi-dimensional array, and if the libraries implement the algorithm with this mdspan thing, then you can pass mdspans between libraries. So what is it exactly? Actually, it's do we have it yet? Maybe. So there's this thing is a copy from CPP reference. There's an overview of which pieces of the C++ standard are already implemented in different compilers, or in different standard libraries in this case, because it's a library. So the first one is the GCC library. It's not implemented currently. The second one is the Clang standard library, and it's almost there. There's actually Microsoft has it already, but if you're not using that in HPC, it doesn't help a lot. And then there are other libraries that I have no clue what they are. They're probably not implementing it ever, and they're probably not used. So it should be there since C++ 23. It's standardized. It will come, but currently you have to rely on some prototype implementations. The one that I was using to make these slides is the implementation from the Cocos library. And it's actually, I think, the implementation from the Cocos library is what is going into, or what went into the Clang standard library. So I think we mentioned sometimes that new C++ features, they go into the standard by writing a paper, and here's actually a link to the paper that describes what it is. It's hard to read, it's very long, and all this started in 2015, took 18 revisions until it was finally standardized. And here's the link to actually how it looks now in the standard. It's also difficult to read. But basically what you can think of mdspan is it's a pointer plus metadata, basically. Pointer plus how you access it. In practice it's a bit more complicated. It's actually this thing, so it's a templated class with different things. The first one is the element type, and then we go through this list and understand a bit better what it is. Will not be very deep, just to get you started and to convince you that if you are implementing such a library that deals with multidimensional data, you should probably use this. Okay, a bit more in detail. So T, I already said, is the element type. And here is, let's start with this example. So how can you construct an mdspan? Here, okay, I said in the beginning it's non-owning, so it doesn't own data. So you have to get the data from somewhere. So you have to allocate some data, and one way to do this is use std vector, because it gives you a continuous block of memory, right? So you allocate 100 space for 100 floats, and then you can take out the pointer to the data with dot data, and you construct your mdspan by passing in the data, or pointer to the data, and you're telling it how you want to interpret this linear data. Here you are saying these 100 elements, they're actually not 100 linear elements. I want you to think about this as a 2D array which is 10 by 10. And this simple example is very simple how you can construct it, right? But as we will see, you have many choices on how to actually customize the behavior, or what mdspan thinks what it is, right? What the view is that you get on the data. Okay, I said already in this example, so extends, this second thing here is what describes the number of dimensions and their sizes. And here it's just saying a class extends. Looks like you can pass whatever you want, but the standard says you cannot. You have to pass something that is a specialization of std extends. So we'll have to look at this in the next slide. You can describe a layout policy. The default is layout right, as you can see here, right? I will tell you later what that means. And you can specify an accessor policy. By default, we use default accessor. And I will have an example on that later. Okay, now we have this view. What can we do with it? We can use it down here. So we have this square brackets 2, 3, which means first index 2, the second index 3. We put the number there. It's simple. And this is also actually you can do this as a C++23 language feature, because before C++23 you could not have operator square bracket with multiple arguments. So this is C++23. In the past, probably, if you have seen these multidimensional array libraries, probably they use the call operator for doing index access, the round parentheses. Okay, well, I didn't say what the default accessor does, but basically it does point to the reference of whatever you're pointing to. Okay, let's look a bit more into std extends. I will not go into too much detail. So, but basically it allows you to describe the extents of your array, and it allows it to describe it both runtime and compile time extents. Right? If you have compile time extents, compiler knows better what knows already what the sizes in these dimensions are, and could potentially optimize. So, if you know your sizes, for example, if you know you are dealing, I don't know, with a field of 2x2 matrices, so the whole thing is, I don't know, let's say 3-dimensional, one dynamic extent that describes your field extent, and you have on each point a matrix of 2x2, then you probably want to describe this 2x2 part with compile time extends, because all the operations that are now doing this, they can be optimized. We already saw constructing this is very simple, but only because here we are relying on class template argumented deduction, because actually it could be, if you look at what extends actually is, it's slightly more complicated. You have one more. I will skip that. It's probably not interesting here. Why you want to specify as index type is. I'll say it. So what is index type here? Index type is basically what type do you use for your indices, and if you and the default here is the default written here. No, the default is size t, which is an unsigned int. Unsigned ints have a specific property. They wrap around. They have well-defined wraparound semantics. But for example, ints don't have this, so it's actually undefined with what happens if you go over the range. So the compiler doesn't have to take care of this wraparound semantics. So in HPC you probably don't want to use size t, but you want to use int, because compiler can do better, right? That's why this customization of the index type is actually went into this mdspan thing. Other than that, I mean, you're specifying here the extents. So the extents itself are described as a non-type template argument of size t, and the requirement is these things could be either std dynamic extent or a number that is representable as index type. So if index type is size t, it's trivial. If it's something else, you need to make sure that what you're giving here is actually representable in this thing. And these numbers that you give here, like which are not dynamic extent in this template instantiation, they are the compile time extent. Okay, some examples. There are different ways how you can construct your extents. Here, say I want index type int. I have a dynamic extend. I have a compile time extend of 3 and another dynamic extend and another compile time extend. Now I'm instantiating this type, and what I have to provide here are the dynamic extends. So the 42 goes here at runtime, and 43 goes here. And here's some code that checks that basically. Okay, so rank 4 extend, there are 2 dynamic ranks, the static extent of 0, so what is this? The static extent of, static extent 0, the first one is actually a dynamic extent, so we don't know at compile time what it is, but we know it's dynamic. And then we can check that the runtime extent, this is correct. Okay, runtime extent of this thing is actually 42, and so on. What else? Okay, there's 2 compile time extents, easy, and then 2 runtime extents constructed in this simple way, as I showed in the beginning. Not super interesting. Because of there are many use cases where you only have runtime extents. There's another special thing, it's called dextends, stands for dynamic extends. So if you have only dynamic extends, you don't have to write this big type. But I'm not sure how useful that is if you can actually use class template argument deduction like in this way. Probably the only use case now is that if you want to specify the index type, then probably you have to use that. Okay, extends. What else? Layout policy. Layout policy describes your memory layout, or basically your index, how you index your memory. And the default, as I said, is the layout right. I didn't hear that description of a layout in any other context than the C++ standard. I don't know, maybe C++ wants to be special. Usually it's called row major or C layout. Why is it called layout right? Actually, I like the name because if someone says row major, I never know what it is. If someone says C layout, I'm used to it, I know it. But layout right is actually nice because the stride 1 index is the rightmost index. Right, so in this picture, this arrow means in which way the linear memory is laid out. So you start from 0.11 and then you increase. If you go to the next memory position, you go to 1, 2. So the rightmost index is increased first. And then you have other policies provided. Layout left, simple, right? Column major or Fortran layout. You go like this. So the first index is increased if you go in memory order through your matrix here. And then you have layout stride, which is a generalization where basically you can provide the strides that you want. And then you can do more special stuff. You can have completely custom layouts where you, for example, skip elements. Layout stride, you will always go through all of them. Probably, I don't know if you can specify, I don't know, maybe you can specify a stride that is not one. But okay, you can definitely do custom layouts. This could be good if you want to implement some tiling algorithms. And you can also map multiple indices to the same element. So you're really flexible on what you can do here. And yeah, that's it. Here's an example of how you can do layout stride, how you construct an mdspan with strided layout. Here I specify, I'll pass in some pointer and I say, okay, the extends actually of my multi-dimensional array is 2, 5, 10, but the strides are, stride 1 is actually the middle one. So here, then this has size 5, so the next stride is 5. And then the last stride is 10, which is this 2 times 5, right? And here's checking that actually our linear memory maps to this index. Here's another example why actually this is useful. And this is taken, I think, yes, taken from the paper that proposed mdspan. So you want to do something here. You want to do matrix vector multiplication, and depending on which architecture you are, one layout will be better than the other. Like on CPUs, you probably want to do C layout because then the inner loop here is vectorized. On GPUs, because of coalesced memory access, you want to use a Fortran layout. So basically, the only thing that you need to change in this algorithm is the layout here, the layout for your 2x2 matrix. And just because Peter very well prepared this slide for me without even seeing it probably, because he introduced all the stuff that is here. So here's a iota view of the range, which is the outer loop, the 0 to n. And then we can do here for each with execution policy which says parallel unsequential, so you can do any point independently. And we do this over this range that is specified with this thing. and we pass in what we actually do. This is the inner loop of the, so this is, the outer loop is the loop for each output index, vector index, and the inner loop is actually doing the multiplication for that index. Yeah. Makes sense? Accessor policy. Don't want to go into detail. This is how the default accessor looks like. An accessor has to provide these 4 types and these 2 methods. The important one is the data handle type. They don't talk about pointers in mdspan, they talk about data handle type. In the simple case, the data handle type is a pointer to element type. And then if you want to access your data, it goes via the access method, and you just do whatever the P is, data handle type is, and you dereference it at the location I. This is the default thing. Why is it useful to customize? There's one example here that's quite interesting, what you can do. So I have this special accessor policy, or special accessor, which I called host device protector. This is the idea here is I can tell the in my accessor policy if this mdspan that I'm constructing here wraps or it creates a view over a CPU memory or a GPU memory, and if I do it wrong, it will give me an error. And so basically what I do is I copied the default accessor and only changed this stuff here. So if you do CUDA programming, you probably have seen it, otherwise it's not important. So here I'm basically saying if I am on compiling this for the CUDA device, then I assert that actually the device here is device type CUDA. In all the other cases, when I'm not compiling for a CUDA device, I assert that actually the device type is CPU. It's a very specific thing now. And then if I do this, I allocate some CUDA memory in some way. And now I am accessing it. Okay, then I create the mdspan, and here's a typo, I guess, right? Because I should create this with device type whatever, CUDA, and now I access it here on the host, not in the CUDA kernel. It will print this error message, which is so this is actually the CUDA, and this is okay. It doesn't have the correct device type. If I would put this in the kernel, it would work. So a compile time check that you're actually accessing your data on the right device. And this is already the summary. So where are we in C++ with multi-dimensional things? In the beginning I said, okay, you have 3 things that you're usually doing on your own. You're writing your allocation of multi-dimensional data, how to access it, and what to do with the multi-dimensional array, the algorithms or whatever. And now the mdspan basically gives you how to access the multi-dimensional data. You still have to allocate your data yourself, and you have to write your own algorithms. There's nothing in the C++ standard library that helps you really deal with multi-dimensional data. But at least for the allocation, there's something in the work. It's likely to go into C++ 26, so we have to wait still a few years. This will be called probably std md array, so it's the owning counterpart to mdspan. And then there's something that's also probably very useful to write your algorithm sub mdspan. You have an mdspan, you want to create a part of it. If you're used to NumPy, for example, it's basically slicing your NumPy array. It's another view on your view, kind of. And if you want to, this is interesting, you want to hear something about algorithms, there's an interesting talk from CPP North last year by Price Lelbach about the title Multidimensional C++, and he's talking about how you could potentially write generic algorithms for multidimensional data. Yeah. If you want to see one more slide with code, it would be that. It's basically, probably you have your own multidimensional array, and now what you should do is you should provide some way to get an mdspan to your data, because then your allocation part, is owning MD array thing, can be used in other libraries that want an mdspan in their interface. Any questions?
What should I use today to store my dense and possibly sparse matrices, given that this is a feature that is not fully implemented in all the standard libraries yet, and maybe I can't upgrade to the latest compilers yet?
I guess if you're starting from scratch, you should probably try to find a library that is working on giving mdspan support in the future, right? Because then you are future-proof. I don't have any experience with this kind of libraries. Like I don't have the overview. I don't know if someone here has a good overview. Maybe the answer is Cocos. Yeah, and this is definitely the case for dense matrices. For sparse matrices, probably you can also create a view for sparse matrices with mdspan. I have no idea how that looks like. I don't know if there are any implementations. I mean, it's flexible, and I think you can do something. I don't know how useful that is. So it's not an answer to the question, but it's giving a link to what I just talked about. Do you have a better answer to your question, Mikhail?
No, so I mean, I think my answer would have been use Cocos today. It's the one I know best myself. They're the ones, like the development team behind Cocos are the ones who proposed mdspan, and they're in fact integrating mdspan into the Cocos library as well. So they have an abstraction that looks very similar to that, Cocos views, that they use to sort of guide the development of mdspan. And there are some other reasons to use Cocos today as well. They have quite a nice programming model for running on GPUs and CPUs as well. So you get both the data and the sort of compute part. Outside of Cocos, I'm not really sure. But
and also,
I don't think you can go wrong with Cocos.
We have an expert in the room, right? I mean, this is the is the paper that proposed mdspan, and this. One of the authors is here.
Yeah, it was many years ago. So one of the features of the mdspan was to allow customization by vendors, right? C++ doesn't want to provide any features that only NVIDIA needs, for instance, just to make one example. And so the idea was to be able to customize, to provide a way by which a vendor can say, allocate the data in my address space, in the device that I have. And so the vendor makes available the implementation that allows you to use the hardware. And that is still there, right? You can also do that. There are some things that I don't particularly like about this proposal, the left-right thing. For me, that I never understood it, but it was a long discussion, long discussion. Some of the language features that you see here came from this proposal, like the square bracket to allow to specify more arguments. And another language feature that was proposed, I don't think that passed, was to allocate. Oh, you could actually use the allocation. You could allocate with the square bracket instead of calling the constructor with all these long types. But that did not pass. Otherwise, you have seen it here. So what to do now? Cocos is the library that does it, and that allows you to use different devices. And but you see, it's quite complicated, right? Because it allows you to really do whatever you want. And doing whatever you want means also you can also do the wrong thing. So it might actually be slower. And the strided axis is general. You can have tiled layouts. You can do whatever you want. You can really make your own, but it's not easy. It's very complicated to use. So once it is set up, you just want to use it. But again, multidimensional arrays are difficult, right? As you probably are aware of the fact that if I have a linear array, using the cache of my computing system is not super difficult. But if I have 2D array, it gets more complicated. If I have a 3D array, it gets very complicated. So the more you add dimensions, the harder it is to get efficiency out of it. This is why having generic algorithms on these things is very difficult. You can have generic algorithms, very easy, but they're going to be slow. So at the end, and for sparse data, then I don't see any other reason that any other way of having some other way, because even if I can express random access with IJ, I need a layout that checks that I'm actually hitting a value and not a zero. And I need to do some search in order to find the I and J. So random access is good for dense algebra, but if I have a sparse one, this thing, in my opinion, does not work.
Yeah, about the sparse thing, there are other libraries that have support sparse, and the problem is much more complex and difficult even to express than the dense one, because you can have it depends on what you want to do with the sparse matrix. You might want to have a fixed support that you freeze and you store efficiently and you just do matrix multiplication, or you might want to have a banded structure, and then the optimal structure changes depending on that. So you have to look at your problem, the available library, and choose the one that fits your own. It's more difficult.